Alrighty, at least one person showed up, so we'll make a start. So today we are doing some more problems to do with electrostatics and whatnot. So last week we looked at the inductive field EI, right? So we had our two rings and we had current, time varying current through one, which generated a magnetic field. And the magnetic field, because it's time varying, induced some sort of force on the electrons in the other conductor. And so we have our EI field, and then the moving the charges in the ring have a Coulomb field as well. So it's time varying. Yep, that's what we did last week. And then we also had the example where we had the magnetic field, and we had our ring moving through it, multiple stages. And so as the ring moved through, we evaluated it at multiple points, but along multiple lengths. So we had some flux in here, right? And that generated some EMF, so we had a potential difference between those two there. And we did some calculations to find out what that EMF and whatnot was. And then when it was inside the field, the potential difference across those 2 points was the same. So we had no EMF. And then finally on the other side, similarly we had some sort of EMF at the end. And so we had our two equations. Well, last week we had the potential difference is equal to minus IR plus ET, and ET is IR. And we saw some of the aspects that come out of that. So today we're just going to be looking at some more problems related to this. So first problem is looking at capacitor with a dielectric material. So you might remember me saying a few weeks ago that this could be something that crops up in an exam, so it might be good to understand these examples. And so again, we want to derive an expression for the electric field and electric potential in the following region, right? So we want to get an expression for EC. How do we get EC? Well, we need to know the potential difference. And we can create some sort of expression of the potential difference using Laplacian. So that is equal to 0. If we look at this capacitor here, it's essentially got a battery attached to it. So we'll have positive charges on top and negative charges off the plates. And so we're going to have a fields going this way, all the way across. And we're going to see what the different dielectric materials, and hopefully by the end it sort of makes sense what comes out at the end. But as you can see, the field here is only in the z direction, so we're only going to have d phi squared dz squared, right? We're only going to have that component. And so we can find some sort of expression, C1z plus C2. And we can use our boundary condition, so what's the potential difference here and what's the potential difference up here to get our values for C1 and C2. And we might end up with something like this in the z direction, or sorry, with z. And I probably should have drawn this out first, but details. So just put that up here. V0 on EZ, where E is that separation distance. Right, so just drawing this out a bit more. So remember, if we have a battery here, it's going to push the positive charges to the edge. I should draw that a bit closer, to the edge of this plate. And the negative charges are going to be pushed to the edge of the bottom plate. And inside, we're going to have no charge density. So there's going to be no charges in there. Right, so once we have our expression for the potential difference, then we can find EC using that. That will give us some expression. And then we can find the charge density as well, which is going to be the E0 EC. And we can use that to find what we actually want, which is the capacitance of the structure. So that is equal to rho S A, and C is equal to Q on V. Right, so we can get some sort of answer for Q and then put that over V, of Q over V, and we'll get some capacitance. And hopefully it'll be in terms of just physical constraints. Won't be anything time varying. Does that make sense? Well, you're the only person I got to ask, so. Again, we've got to put our assumptions in. So it's a uniform field of XY between the plates, no field outside the plates. Different densities of charge on materials. So each of those materials will have their own rho, right? E1 and E2. Positive on lower surface of top plate, negative on the upper surface of the lower plate, based on the properties of a conductor. And yeah, so we've got our system like this, and there could be 5 different boundary conditions in this case, right? So we've got this plate here, what's happening there, what's happening there, what's happening here, here, and then what's happening here. So a boundary condition whenever something changes, right? So we're going from conductor to dielectric, and then dielectric back to conductor. This is going between 2 dielectrics, and so on and so forth. And we're going to look at just working out the values for this, right? So the hypothesis, charges are shown and the field is uniform in X and Y. So X and Y, the field is going to be like this, only in the Z direction. We consider the boundaries at Y equal to A, so at this point here. We know that the field, the electric field at 1, at A, is going to be equal to the tangential part. So if we look back to earlier where we had, that's our field, we have some sort of surface in there. It's normal in this direction, so the fields line up. And so this is the field captured by the surface, and that's going to be what we called flux, right? But if this surface, we can also have a tangential component, right? So this is the normal part, and this is the tangential. If we put this field again, and we put the plate like this, so now the normal is this way, it's going to be tangential to that. And so the field, that's all it's saying there, is the tangential part here is equal to the tangential part on both sides. So I'll scribble that out. And so this field here and here are going to be equal, right? So let's start by looking at getting some sort of, let's see if we can get some sort of expression for the charge density. So consider the upper boundary between metal and dielectric. So up here, between 0 and y is equal less than a. So we're considering the upper boundary just above E, or just past E. So we've got our metal and our dielectric, and from previous lectures and whatnot, you'll have that D1 minus D2 is equal to the charge density. And so we can rewrite it like this here. But we know that for any of the metals, that the charge density is going to be 0, right? So at the edges of this plate, right? So all the charges have been built up on the edge. So the charge density inside that metal plate is 0. Whereas the dielectric material is different. The charges are sort of induced, but there's still some density in there. So the effect of that is essentially that we get this out here, where the charge density is equal to E times E1, where E1 is just the property of that dielectric material. If it was free space, we'd just have that the charge density is equal to E naught E. Right? And that's similar to what we had in previous weeks. And again, we can look at that expression for the lower boundary, and then we can look at it for the other side as well. And so consider the upper boundary between metal and dielectric, but this time for this side here, and we get the same sort of expression coming out. Hopefully nothing too scary there. Also, due to the metal plates and applied sources, they have boundary conditions. So on these plates here, we have some battery connected to it. It's going to make this V0 and this 0. So at Z0, we're going to have a potential difference of 0, and at Z equal to E, we're going to have a potential distance of V0. Assume that the potential difference does not depend on X and Y in this space, which is a good enough assumption. Need to confirm that the solution meets the boundary conditions, so do take the Laplacian of that. And obviously we've got the field doesn't depend on Y or X, because it's only in the Z direction. So we're only going to have that second differential there. And because there's no free charge, that should equal to 0. Alrighty, so got these conditions here. There's no free charge in the region. So we've got our second derivative. That means we've got some solution equal to this. If we take our boundary conditions, we get that C12 is equal to 0, and that C11E, so E being that distance that it's traveled, is equal to V0, right? And so our electric field, this one here, is equal to negative derivative of that. And so we find that we get that the electric field is V0 over E, which is the separation distance, and it's in the direction of negative AZ, right? So we got the field is coming down this way, right? We then times that by this E1, and it's going to get rho 1, right? So that's our expression for this side here. For the other side, again, follow the same thing, and we get that it's similarly this here. The two equations look the same, so we check the boundary conditions 1 and 2, and these two are equal to each other, which is consistent with what we said earlier, that the tangential components have to be equal, right? The total charge on the upper plate is going to be this, so we've got that the charge is equal to the charge density times the area plus the charge density times area 2. The area of that surface is just going to be B times D, right? If we go back, did that show that? No? Okay, never mind. All right, so we've got the charge density A times D plus B times D. Then we just substitute in our equations from previous, right? We come out with this sort of expression here. If we then substitute that into our value for capacitance, right, then this will cancel with this, and we're left with D on E all times this. And if we split that out, right, got E1, epsilon 1, AD on E plus epsilon 2, BD on E. We might find that that's just going to be the capacitance of the individual capacitors, right? So we have capacitors C1 and C2, right? And that's what they're defined as. And what we note from this is then that if we look at this visually, go back all the way, yeah. If we look at this here, we've got C1 and C2. If we break that up, we can see that these are in parallel to each other, right? So capacitor like this, capacitor like that. And so it makes sense that, if you remember from fundamentals, when capacitors are in parallel, they add. And that's exactly what we're seeing here. When we've got two different dielectric materials, we've got two different capacitors, but essentially they'll still add up. Does that make sense? Yeah. I don't think these equations or anything is too hard to follow, right? It's the same steps. So this time, we'll do a second example, and the second example looks slightly different, right? So we have our two plates again, connected to our battery. So we're going to push charges to the surface of the conductors. Then we've got three separations, right? E3, E2, and E1. So E3 and E1 are free space, and E2 is going to be a dielectric material, right? And so we want to determine the electric field and the electric flux in the dielectric and free space regions, and then we want to work out what the capacitance between the metal plates. Right? So have a bit of a think about that for a minute or two, and then we'll go through that one. Yeah, okay. All right, so let's have a look at this one. So we've got our dielectric material, we've got our fields here, so we've got the displacement field, D is equal to the free space permittivity times the electric field, E1, displacement field D3, same thing, and then displacement field 2 is going to include P2, which is the induced field. So if you remember from dielectrics, or from when we had before, if we had some sort of field here with plates, charges on them, and we had some sort of induced charges here and here. And so we had this new field in here, which was that P field, right? And that can be written as E as opposed to E naught. And E is, well, you can go back and have a look at the notes, but essentially it's the electric field generated by the two plates plus the induced field from the dielectric material, right? No free surface charges on dielectric materials, so thus we have that the displacement fields D1, D2, and D3 are all equal. And the surface charge, the charge density is the surface charge density on one of the plates. And then we have just some more of the other equations that we have there. So if we look at the example, we're looking at the three regions of interest, right? We've got our plates, we've got our charges built up in the dielectric material, creating our second field. Our P1 for the free space is going to be 0, there's no induced fields, but P2 is going to have something. And so our displacement field is made up of those two. The potential difference between the plates is given by this equation here. So it's the sum of the potential differences times D. So D1, D2, and D3, the separation between them, minus the initial potential difference, right? So potential difference at 0, and this could be a 0 point here, so something like that, right? But because we've connected it to a battery, that potential difference at 0 is just going to be 0. Right. And so our electric field is going to be this integral here, and I don't know why, but the notes have it written twice in a row. But we're integrating between 0 and D1 plus D2 plus D3 of Ex x dx. And we can separate that into the three separate integrals for each section, E1, E2, and E3, because we can get a field for E1, E2, and E3. And E1 times D1, right, because it's between 0 and D1 over X. So we're just going to get E1 D1 minus E1 times 0, which is going to be just E1 D1, and so on for the other two. And then we can rewrite the electric field E1 to be Q'd on A. So the electric field is going to be equal to charges over like that, which I think we had from 2 or 3 weeks ago. So if you can't remember that, just have a look back at that. Right. Then we substitute that into our equation. So we'll have Q over Q D1 over A E naught plus Q D2 over A E naught plus Q over Q D3 over A E naught. And obviously all the Q's cancel out. And we're left with 1 over this. And as we said before, C is equal to the distance between the two plates divided by the area times the material permittivity, or E if we've got dielectric material, right, because there's some induced. And so we've got capacitance values C1, C2, and C3. And if you look at that, you can sort of see then that for this configuration, it's like we've got capacitors in series, right? So if they're in series for capacitors, then we add them up similarly to how we have parallel resistors. We do the same thing for capacitors. And yeah, so hopefully that's not too hard to understand, because it's just solving the same sort of principles there, just in a slightly different way. Did you have any questions on that one? No? All right, and the final one we'll do today is just a dipole example. So when we're talking about dipoles, we've got our charges here, our two sides of a magnet, north-south, right? And that's generating some sort of EM field going out. And if we look at that in sort of the R direction, right? So if we take the spherical coordinate system, we've got two angles and we're heading out on the radius. We'll have this EM field generating a magnetic section and an electric field section. That's going to be propagating out like so. And we can sort of split this up into two sections. We got near field and far field. And for most of the stuff that we're doing, we're mostly concerned with the far field because we're sending signals over extended space. So we've got two antennas and we're trying to send away from one to the other to send a signal, which is definitely for the far field, right? And so we get these equations. Don't worry too much about where they come from. Just know that we have these equations, one's for the magnetic field and one's for the electric field. And if we look at this and we go, okay, for the magnetic field, we've got something related to R and something related to R squared, and it's going to be in the A phi direction, right? So it's going to be in the radial direction, this direction here, right? So if we look at that, we can say it's something, we'll just call it A on R plus A on R squared, right, for simplification purposes. The further out we go, the larger R becomes, and the smaller this value gets, and therefore this becomes the dominant term. Does that make sense? And so for this case then, we'll have that this side here is going to be our far field, and this side here is going to be our near field, right? Because we can split this up because of the fact that in the smaller radius, this term plays a bigger role, and then as we move far away, this term becomes the more dominant term. And so we split it up into those two regions. Similarly with the electric field, we have R squared and R cubed, and obviously the R cubed value is going to get smaller a lot faster. So when we're looking at these questions and we're looking at far field, which is mostly what we're concerned with, we end up being able to just ignore these other sections here, all right? So if we graph those values, the amplitudes of them, you can see that the 1 on 3 term drops off very quickly, the 1 on R squared term drops off relatively quick, and this 1 on R term becomes the dominant term, which is where we have our far zone. So we have our near zone and we have some intermediate zone between the two. All right. And so radiated or far field is associated with the 1 on R. The near field is associated with 1 on R squared, and also with the R cubed term. And it sort of comes from induction and transformers is where that's sort of relevant. Otherwise, we're looking at the far field values. All right, so if we take that and simplify it, our equation becomes this, and we're just going to call it H. Oh, sorry, we've got the magnetic field, which we're going to call H, right? So we've got this E term and the H term. Yep. And what we can then do is work out the power. So if we wanted to know the power of that radiated field, we take the electric field cross product with the magnetic field, H, and we get this here. And obviously the electric field is in the up-down direction here, and the magnetic field is in the phi direction. And if we take the cross product of that, remember the cross product, the resultant is going to be in the perpendicular direction to both of those. And in our 3-coordinate cylindrical system, it's going to be in the direction of AR, right? So this AR is the power. If we take the time average of that, we get the pointing vector. So this here is called the pointing vector, all right? And so that tells us the power in a particular direction from a dipole that's radiating. So propagated fields propagating with speed c in direction r. The fields are mutually at right angles to each other, right? Because they're in two different directions. And they're both at right angles to the direction of propagation. So transverse electromagnetics. So now let's say we've got our antennas, and we'll do this in a minute, but we've got our antennas here, and we want to know what the total power here is, right? We might be calculating it to work out if our antenna is going to be powerful enough to send a signal there or something like that. So we'll take the integral over that space for this vector here in order to determine the total power at that point. Before that, we're just going to work out, we can also work out the resistance of the free space. So first, we'll just change everything to, so we can represent our fields, our voltages and currents like this. But this is also, we can put it in the complex plane like this, right? So we're doing that on the next slide. So in the next slide here, we're trying to work out what the resistance is. And remember, V equals IR, so R is going to be V on I. We've got our two fields. So in this case, for resistance, we look at this, but for the impedance of a wave, we're looking at the electric field divided by the magnetic field, right? So for free space, this is going to be equals here. For free space, the resistance is going to be this field divided by this one. Put your values in, and you'll get that the resistance for free space is 377 ohms. All right? Similarly with the power, as I said before, we can take our pointing vector, we can take the integral over that closed surface, and look at the total power radiated at that point over that surface. So we take the integral of that, and we get this out here. And that's sort of it for today. There wasn't really a lot. Was that all clear? It's mostly just substituting numbers in, and I believe Professor Hill is going to do a lecture on it today or tomorrow. If you went to the lecture today, he might have covered it today, or he's covering it tomorrow in more detail. Unfortunately, the practicals are supposed to be revision of what you learnt, but it's hard to revise something that is a little bit behind in the lectures. But yeah, so it's just sort of looking at like the properties of far and near fields, but specifically at far fields, because that's what we're probably more interested in. And we're interested in looking at the power at that location and the resistance through the material that it's moving through. So that's just sort of how you would calculate those values. And it might crop up in the exam where you've got to send a signal X amount of distance. So you might have to work out like what the power is at that point and see if it's viable or something like that. No questions? No. Okay, we'll leave it there then.